It's true, yeah. So you can check chapter 1, we already have the frequency hopping spread spectrum. But right now, we still already have these. If we want to have an orthogonal code, how can we construct the orthogonal codes? And in fact, we have 8 orthogonal code, but the orthogonal code here we call Walsh codes. Well, so if it is Walsh code, you can check. How about first one and second one perform inner product? Can we have a 0? Inner product. Yes, we have an integral and multiply the two signals S1 and S2. So we should have a 0. Is it true? Yes, right? And actually, this is a waveform to perform the inner product. We should have an integral and the integral for the integrand of a product for the two signals. And so that you will have a 0. However, if we use code, if we use the concept of code, here maybe it's 0 and this one is 1. All right, and this one is 1 and it's 1. Something like this. So if we have the code, somehow like we have the concept, but if we have the code to perform the inner product here, since we know, but maybe it's too simple for me, so we should have these. We have 1 minus 1, 1 minus 1. Actually, we have these. All right. So actually, we can have the code, but the code, if we want to perform inner product, can we use, for example? All right. Currently, we have 0, 1, but later we need to have the transformation to the waveform. To the waveform, then you can have the inner product calculation. I just want to mention something like this, but later we will pass on. For example, this way, 1 and 0. So 1 and 0 here, maybe we have 1, we have 4, 1 and 4, 0. Why that it have these? Because delta I will that it have the construction of we're using the Hadamard code. So this is a relationship to have the orthogonal construction. How to have that? In fact, we can have the covector. Initially, maybe we can have H0 equal to 0. So next one, we should have H1. H1 can be H0, H0, H0. Oh, here it's 1. So the covector like the 0, 0, 0, 1. Or maybe you think, okay, initially we have H0 equal to 1. So the two vector, if we have the waveform, for example, waveform here is minus. And this one, we have minus and positive. So inner product is 0, am I right? Inner product is 0, however, how about the code 0, 0 and 0, 1? Can we have 0 directly? If we have the concept 0, 0, 0, 1, if we use 0 directly, yes, we still can have a 0. Right? 0 multiply 0, 0 multiply 1, still 0. So if we have its row, we have a code coming from the rows. And how about 1? If we have a 1, look at this. 1, and then it's 0. So if we have a 1, 1, 1, 1, 0. Then using the code, we cannot have a 0. But using waveform, we still have a 0. Right? If we use waveform, still we can have inner product 0 property. However, if we use the code to have 0 not, actually we should start from this, and so that you can have the check-in directly. So that's why my suggestion, this one. And so that you can check, okay, the code, they are 0. Right? And understand this. At this, maybe let me stop here to let you check the relationship. The relationship actually, we can have for the orthogonal codes. And the relationship to have for the orthogonal code, how to check orthogonality? We can check waveform. If we auto check waveform, the initial matrix here can be 0 or 1. But if we want to have the inner product using code to have orthogonality, we should start from 0. Is it okay? So at least check this and practice some. And right now, I already have the next one. If how about 2? So I have a different color. You can try this. How about 2? If we have a 2, we should have this. 0, 0, 0, 1, 0, 0, 0, 1, and 1, 1, 1, 0. All right. And right now, check the inner product using code. So how about the inner product for the 2 rows? 0 multiply 0, 1 multiply 0, 0 multiply 1. Oh, maybe. Maybe here still have the problem. So at this code for this one, okay. For this one, maybe not. Okay, so we still need to return to waveform. All right. So if we have for the second one, 0, 0 for the first one and second one is okay. But for the first one and the others, okay. However, for the others, maybe no. So yes, checking orthogonality. We should use waveform. So it doesn't matter. Start from 0 or start from 1, it doesn't matter. All right, so this is a way to construct the so-called orthogonal codes. And orthogonal code, we can represent the orthogonal code in terms of 0 and 1. But finally, we should implement the code in terms of waveform. So you can have a 1 to the level of 1, 0 to the level of -1, and then you can use a waveform to check orthogonality. And right now, we can have H3 as well. So that H3 can be this. We can based on matrix H3 to have the Walsh codes. So you can try. And once you have that one, how to have the first one. Actually, if you want to have that one using 1, you can set 0 to level 1, 1 to level -1, and then it will be easier to have the current waveform. But it doesn't matter. You can have a different way to have the interpretation. All right, so this is a relationship to construct the orthogonal codes using raw vectors of the current matrix. And the current matrix we call it's the Hadamard matrix. All right, you can check the textbook and so that you can find the name of the matrix. It's called the Hadamard matrix. So Hadamard matrix containing the orthogonal row vectors. So we can pass on the concept of a Hadamard matrix to extract the orthogonal vector. If we have orthogonal vectors, we just choose some of them, they still have the property of orthogonality. All right, that's all. So let me stop here again, allow you to have 2 minutes to discuss with your neighbors. Okay, go and check it.
Sorry, does there are minus should be or not? Because in your example, there was no minus before.
It should be the complement. If I use 0 and 1, it is the complement.
Oh.
Minus here means complement. And complement actually, if we convert it to magnitude, then it's minus. So that says I use, actually previous the operation for me, I use 0 and 1, so I use complement. And once I have the results, we should convert it to the waveform, then waveform follow your operation minus. Right?
Yeah.
So once they mentioned, you can look up the internet Hadamard matrix. And Hadamard matrix, the relationship should be complement or minus. If we use positive 1 and minus 1, then it's true. You have a minus directly. But right now I use binary 0 and 1. So I use the concept of a complement. Once I have the complement, if I should have the waveform, you need to convert it to positive 1 and negative 1. And so minus and the complement, even the two operations, they are different. However, finally, if we check waveform using the actual operation, for example, maybe we should have the complement, then we have the transformation from 0, 1 to positive 1 and minus 1. Then finally, about the waveform, we always have the same waveform. And also about the mapping, should we map 0 to 1, 1 to 0, 1 to 1? No. Maybe you can reverse it. Oh, okay, you prefer 0 to positive 1 and 1 to minus 1. That's okay as well because it's just a notation. All right, so this is a way to construct. For example, here we can have a Walsh codes. But how to have a Walsh code to have the orthogonality? We can pass on the relationship of a matrix, Hadamard matrix. The Hadamard matrix allows us to have the orthogonal vector to check row vector. So you can extract row vector from the Hadamard matrix, then you can have the orthogonal codes. So this is the current concept we try to let it have. Well, no further questions, right? All right, that's all. So how to have an orthogonal code, for example, to have a Walsh code, you can pass on Hadamard code. And Hadamard code to check the orthogonality. We still need to have the waveform. I saw that this is a way to check inner product. We have signal waveform, multiply signal waveform, and perform integral during the period. I saw that if you have a 0, then you have the orthogonality. They are orthogonal. Or otherwise, no. But you should understand sometimes the waveform, perhaps we can have the distortion. So maybe near 0. And how to have the further operation, actually you can check if we don't have the perfect one, and then how to have the operation so we can round it out to have the final result. Or otherwise, we already have the signal. So all less than 0, so we ask him, okay, now orthogonal. It is not okay at all.